Title of the talk is Measurement of Higgs coupling to quarks by Lucas Yukawa. Let me give a brief introduction of our next speaker. Lucas is a staff researcher at CERN working on the CMS experiment. He received his PhD from University of Athens. His research interests are focused mainly on the search for physics beyond standard model and measurement of Higgs boson properties. He played an important role in searches for SUSY partners of the top quark, for Higgs boson decays to pair of charm quarks, and for Higgs boson pair production in the high momentum regime. In parallel, he has been highly involved in the development of missing transverse momentum reconstruction and jet tagging, particularly with novel machine learning algorithms. Finally, I would like to say that he's very active in the CMS Phase 2 program, focusing on the upgrade of the end cap calorimeters with the high granularity calorimeter. And thank you, Lucas, for accepting our invitation. Please go ahead with you.
Thank you very much, Seema. Thank you very much for the kind words, and thank you very much for the invitation. So let me share the slides. I think you should be able to see them now.
Yeah, we can see.
Let me make them also full screen. Okay, and move also the panel. Okay, so it's a pleasure for me to talk about to give an overview about the efforts the last 10 years since the discovery of the Higgs particle on measuring the Higgs-quark interactions. So just for completeness, I will start with a very brief introduction. I'm not going to go into the details of the theory since they were already discussed a few times already the last few days. So clearly the highlight after the first data-taking years of LHC is the discovery of Higgs boson with mass around 125 GeV. This happened 4th of July 2022. And the discovery of the Higgs boson completes the standard model of particle physics. And standard model is a very elegant theory. It can fit even in a small cup. So the first two lines are physics that we know already before the discovery of the Higgs. The third line describes the interaction, the couplings of the Higgs particle with fermions. And the fourth line describes the interaction of the Higgs boson with bosons. So, and these are priorities of the LHC program to measure these interactions. So, since the Higgs boson is the only fundamental scalar particle, at least observed so far, should be playing a very special role in the standard model. And actually, the discovery of the Higgs boson is not the end of the story. It's actually, on the contrary, it opens a whole new chapter of exploration. And just to give you a couple of examples, we see different new physics model, BSM physics model, how they can modify the couplings of the standard model of the Higgs boson with other standard model particles compared to in the case of the absence of new physics you see here. So we can modify the rates and the couplings. We can also modify the presence of new physics and modify also the differential distribution. And I show here an example how the PT Higgs would look like if there was no new physics. And for instance, with red or with blue, these are different BSM models, how it can be modified. And the modifications are particularly important at the higher PT Higgs regime that for these specific models can be like a factor of 4. So for all these motivations, the LHC experiment, particularly Atlas and CMS, are exhaustively studying the Higgs boson properties. And today, as I said, I'm going to give you an overview of the main efforts carried out since the discovery of the Higgs boson on understanding the interactions between the Higgs and quarks. And also, I will also show some highlights on development on the tools, particularly jet tagging tools that allow us to reach to meet these goals. So, as I said, the theory, I will just go very quickly, but just to set the scene, when we talk about Yukawa couplings, we mean about interaction of the Higgs boson with fermions, quarks or leptons. And the strength of this coupling is proportional to the mass of the fermion. So the stronger one with a scale of 1 is the Higgs and top. And then since the bottom, charm, etc. are lighter, this the coupling strength can be much lower, that spans several orders of magnitude. And the question is, who ordered that? So as you know, the quark masses are not predicted from the standard model, are parameters of the model. And it's a priority of the LHC physics program to measure as many and also as precisely as possible of the Higgs quark couplings, because deviations in the couplings can be, as I showed earlier, can give strong hints of the presence of new physics. So Higgs, there are multiple production modes. The most dominant production mode is the gluon fusion one, has a larger production rate, but also one has to, in this production mode, one has to fight with huge QCD background. Another one is the vector boson fusion, which is almost an order of magnitude smaller than the DZF. Still, QCD is large, but the presence of the two forward quarks can provide means to suppress the QCD background. And then we have other production modes, like, for example, the associated production of the Higgs and the WRZ boson, which has smaller rate, significantly smaller rate, but on the other hand, one can use leptonic decays of the W and Z's to suppress to negligible level the QCD background. And then, of course, we have TTH that I'm going to discuss also later, another more rare production mode. And then concerning the Higgs decay mode, the dominant one is when the Higgs decays to a pair of big quarks. This is almost 60% of the total width. And then we have decays to charms, which is around 3%. And then, of course, since it depends on the mass, going to strange or first generation quark, this goes, the branch ratio goes as low as 10 to the minus 5. So we're probably, these decay modes are, at least directly, it's difficult to explore at the LHC. And just to give you some numbers about the yields we're talking about, let's take the case where the Higgs decays to a pair of charms. In the gluon fusion channel, we expect around 50,000 events in 36 CMS femtobarn data. And then in the V8, the cleaner final state, we expect around 2,000 events. And just to understand how challenging it is to extract the signal from the background is for TT bar, we expect around 30 million. Right? So now, how we interpret the results, there are a couple of approaches. The more traditional one is using in the terms of signal strength. So here we don't separate between production and branching ratio. So effectively we measure the yields and we compare the production times branching ratio yields, the observed yields, over the value expected from standard model. A step further is to use the kappa framework. This is the simplest framework to probe deviation from the standard model. So effectively what we do and what we describe here is the relationship that we express the mu's, the signal strengths, to kappas. So it has advantages that it's simple and we don't need to do any BSM calculations, but has also simplifications. For example, some details like polarization, etc., is not included in this framework. And then moving to the effective field theory, this is effectively an extension of the kappa framework, but allows us also to probe helicity structure, polarization, etc. And via operators that you see here, EFT is sensitive to higher order effects. So we use these approaches to interpret the measurements that we do. So where do we stand today? So first of all, a very quick reminder, interaction, including production rates and interaction with bosons like W, Z, and photons were already established since run 1. Concerning interaction with fermions, and particularly with quarks, the Higgs-top coupling was established back in 2018 using run 1 data and also data from the 2016 data collected during the run 2 runs. And then the interaction with Higgs, of the Higgs boson with bottom quarks was established by statistically combining results from run 1 and the first 2 data taken in years of run 2. And you see it here, the compatibility. And then the next stop is actually to go to second generation, the interaction of the Higgs with second generation quarks, and the most promising one, but still far away, as you see, is the Higgs-charm. So So overall, this is mind the log scale on the wax range. We have an impressive agreement of the couplings with compared to the standard model values over several orders of magnitude. So, but of course, this is challenging. First of all, we have to fight with very large backgrounds. So it's very easy to produce quarks and gluons in hadronic collider at the LHC, and to get a feeling the BB cross-section at, let's say, at the LHC is not, and I saw it here with pink, and compared to the more the highest production rate GGF channel, which is here. So we are talking about several orders of magnitude. So another challenge is the jet reconstruction and identification. So we have to deal with PyLab, we have to deal with to develop very powerful bottom and charm tagging algorithms, and particularly for the first and second generation quarks, we have also small rates for small branching ratios. So we follow a very, concerning the search strategy, we follow a very comprehensive approach. We have, of course, direct searches targeting mainly the top, B, and C couplings. Then we have exclusive decays for second generation, and also possibly for first generation, and also indirect bounds from other Higgs measurements, mainly to constrain first and second generation. So this is a very clearly, very demanding program, and it requires novel tools and techniques, and of course, in many cases, also the data that we collect at high luminosity LHC. Now, as I said, just a couple of slides, I mean, because this is particularly important when we want to measure Higgs-quark interaction, is the jet reconstruction. And both Atlas and CMS use a flavor of particle flow algorithm, which combines information from several, from all the sub-detectors, and then gives a mutually exclusive list of particles. So, and then we use these particles to reconstruct more involved objects like jets, for example. And the particle flow algorithm brought a very significant improvement in the jet performance. Here is an example of the jet energy resolution. With red is from particle flow, with blue is using calorimetric only information. And then also detectors play a critical role. So, for instance, an example is the upgraded pixel detector that happened in CMS in 2017, had a major impact in the performance of the bit-tagging algorithm. So the green line here corresponds to the performance of the bit-tagging algorithm using the previous pixel detector with 3 layers. The red one is the performance with the upgraded detector with the 4 layers. So one, for the same signal efficiency, one can improve the background rejection by a factor of 2 to 3. And for sure, all these developments are very important in analysis, like for instance, the Higgs to BB. Okay, now moving to the main part of the talk, I will start with the efforts in measuring, establishing the Higgs-top quark interaction. And the first actually hint of interaction between the Higgs and the top, it came in the gluon fusion production, and where the Higgs decays to a pair of photons. And the thing here is that gluons and photons are massless, so you interact with the Higgs only via loops. And in these loops, main contribution comes from top quarks in the case of DGF, and for the case of gamma gamma, we have contribution from W boson and top. So we measure the rates, and if they are consistent with the standard model, this is a strong hint that there is an existence of the Higgs-top coupling. And this is an example, a candidate Higgs candidate event. The signature is 2 high PT photons. This, as you remember, maybe you remember in the plot that I showed earlier, the rate is very small. It's 2 per mil, but we take advantage of the excellent photon reconstruction. The challenges in this analysis is we need to have very optimized photon reconstruction and calibration, and also to suppress significantly the fake photon background. And the strategy is to exploit the energy resolution of the photon. So we fit the invariant mass of the 2 photons to extract the signal. And then there are different analysis categories based on the quality of these 2 photons. And to further suppress the background from the gamma plus Z background, we use machine learning techniques. So this is the result actually shown 4th of July 2012, a couple, 10 years ago or so. And this is an example plot from Atlas, similar result from CMS. So you see here the invariant mass of the two photons consistent with the mass of the Higgs kernel, 125 GeV. And the measured signal strength, it was at that time 1.8 plus or minus 0.5. So a reminder that mu equals 1 corresponds to the standard model value. And this small increase actually in the rate caused some excitement because in the presence of new physics, of particles, of new particles, actually this rate can be increased. However, when we move to the full run-to data, things are consistent, pretty consistent with standard model with a mu very close to 1 and very consistent within uncertainties with 1, right? So we have a hint, a very strong hint that top Higgs interacts with top quarks. And the next step, of course, is to have a direct access to this coupling. And this we did actually in the TTH production mode. This is a very busy, this is an event display of the TTH production. This is a very busy final state. We have B's from the tops. You have multiple jets depending on how many of the W decay hadronically. So the motivation is clear. So TTH can give us direct access to Higgs-top coupling. It's very rare. It's more than 100 times smaller than the TTF case. And the general analysis strategy is that we have two systems. We have the TT-bar system, where we define categories based on the leptonic decays of the W. And clearly here, hadronic top reconstruction and B tagging are very important. And then we have the Higgs system, where there in principle, we can exploit all possible Higgs decay mode, like PP, gamma gamma, ZZ, etc. The challenge in this analysis is clearly the combinatorial background and lots of machine learning used in the analysis design to improve performance. Another production, the TH production is also important. Of course, we are not, we are not as sensitive now as in the TTH, but the advantage here is that it gives us the relative sign between the top Yukawa and the W Yukawa. So the first observation of TTH happened, as I said, in 2018, and this happened by combining multiple data taking gears, all run 1 and the quarter of run 2 data, multiple channels. So we have Higgs decaying to a pair of photons, ZZ, WW, BB, and tau tau. This is kind of a tour de force here, this approach. There are advanced machine learning were used for object reconstruction, but also for the event level separation, and very sophisticated background estimation techniques were developed for this search. So the observation, we observed TTH reduction with more than 5 sigma, 4.2 were expected, and the mu value, the signal strength is 1.3, consistent with the standard model value. Now, the more sensitive channel in this analysis were the TTH to BB and the TTH to 2 photons. So then, since we observed it, the focus is to go after individual channels and production mode. And I will start with the TTH gamma-gamma channel. Here, the strategy is to categorize events, again, based on the leptonic decays of the W, focusing in the 0 and 1 lepton channels. Key points is the photon and top quark reconstruction, and also where machine learning techniques are used to improve the performance, and also to suppress the non-resonant gamma-gamma background, again, using machine learning technique. So the idea is to define categories based on the output of the discriminant, and then for each of these disjoint categories, fit the invariant mass of the 2 photons. And both CMS and Atlas observed this TTH in this decay channel. Actually, this is the first observation of TTH in a single decay channel. And not only that, but I think this was discussed also yesterday, the TTH, we managed to also extract information differentially in the PT of the Higgs and TTH. It's the first time this is happening, and contributes to the global picture where we have in the Higgs to gamma-gamma land, where we have the different production modes in different regions in differential distributions. Now, moving on another decay channel, this is where the Higgs decays to multileptons. The Higgs decays to WW, ZZ, tau, tau. So the signature is multiple leptons and or hadronic taus. Key points of the analysis is to have the lepton identification and also, of course, the hadronic tau and the BZ identification. And a challenge is also the background estimation, particularly the TTV background estimation. Again, advanced machine learning techniques are used to extract the signal. And you see here, the expected sensitivity. This shows the logarithm of the signal over background in different bins, the data distributed based on the S over B, the signal purity they have. And the expected sensitivity in TTH is above 5 sigma. The observed is almost there, is 4.7. So typically we cannot claim an observation, but the right plot shows also the signal strength. So the signal strength is consistent with 1 within uncertainty. And these results are used actually to set constraints on the kappa t, which kappa t is smaller than 1.1. So it's very close to standard model value. The next decay mode that I would like to discuss is in the case where the Higgs decays to a pair of Bs. So this has, as we said, the largest branching ratio, but there are important challenges here is clearly B tagging in a hadronic collider, and also the modeling of the TT bar background, particularly when we have Bs and Cs coming from gluon splitting. And this is due to this challenge. This analysis requires breakthroughs in multiple areas on the object reconstruction and also in the signal extraction. And I would like to highlight particularly the development in the signal extraction. Here, in order to separate signal from the different backgrounds, a dense neural network is used. There are typical inputs, high-level, human-inspired high-level variables like object kinematics, event information, jet flavor, object correlations, etc. But the nice thing here is the output. So we have the output is a multi-class. One class is the signal, the TTH, but then the different nodes of the DNN correspond to different processes. So we have, for instance, different process for TT plus BB, TT plus CC, TT plus light flavor, etc. And this allows actually to have control regions in data that have improved purity. So this allows to better constrain the different processes, which translate to reduce systematic uncertainties. Finally, the signal is extracted by fitting the output of the DNA in multiple categories. So, and here are the results. This uses only 2016 and 2017 data, run-to data. And this is the first evidence, corresponds to the first evidence in this decay mode. So it's almost 4 sigma, the observed significance, with a mu of 1.15 consistent with the standard model value. A point that I would like to highlight here is that the dominant systematic uncertainty on mu is actually coming on the modeling of this challenging TT plus heavy flavor background. And this is an area that both Atlas and CMS experiment, but also the theory, we should put some work on and improve to reduce the uncertainty. Another thing that carried out by Atlas is actually to carry out a differential measurement in TTH, VB. So we see here the signal strength measured in different regions of the PT of the Higgs candidate. And of course, here the inclusive one. And overall, the agreement is pretty consistent with the standard model. Now, the last analysis I would like to quickly show in terms of Higgs-top coupling is the constraints that we can get on kappa t from top physics. So here, actually, there are electroweak corrections, electroweak interactions between electroweak type interactions with scalars between the top and the scalars, for instance, the Higgs, that are so small that if one checks inclusive distributions or cross sections, they are not visible. However, there can be observables like the invariant mass of the top quark that can be sensitive to these interactions. And on the plot here with black, you see the distribution of the invariant mass of the two tops for kappa T1, so for equals 1, that means for standard model values, and the different colors like the green, red, and blue corresponds to different values of kappa T that can be modified in the presence of new physics. So they have a very significant effect in the shape, in the distribution of the ditops and the ditop invariant mass. So based on this motivation, in CMS we carried out an analysis in the lepton channel that actually measures the invariant mass of the two tops and also the difference in the rapidity between the two tops, right? And looks and uses this information to constrain the kappa T. So this is a result of the invariant mass of the two tops in different data taking years of run two data taking periods, and also in different regions of delta of pseudo rapidity, right? And the results are consistent within uncertainty the standard model value. Kappa T is 1.16 plus or minus around 20 something. And we use the result to set constraints on kappa T smaller than 1.6. Now, if you recall on the TTH to MultiLeptons, this constraint is which was 1.1, the constraint on kappa T. This is weaker than the decayed Higgs boson measurement. However, here there are no assumptions on the other kappas. So this provides a model-independent constraint. Now, moving on Higgs-bottom quark coupling. So first I will start that by quoting, taking a snapshot from the Atlas TDR back in 1999. So there was not much hope at the beginning. As you see here, there was very little belief that we are going to observe Higgs to be B at the LHC. As you know, we saw it, so we exceeded expectations here. So this is an event display of the Higgs-bottom of an event where the Higgs decays to two Bs, and the Higgs is produced in association with the Z boson, where the Z decays to two electrons. So this is a very clean back-to-back signature. As I said, this has the largest branching ratio, but the main challenge is, of course, we have to find with huge QCD. You need powerful betagging algorithms, and of course, another challenge is the modeling of processes with heavy quarks like Bs and Cs. And the general strategy here is to exploit multiple production modes. The golden channel is the VH production mode. There has been a lot of effort and innovation in developing powerful betagging algorithms and also developing sophisticated signal extraction strategies, particularly with the help from machine learning techniques. So, as I said, there was not much hope at the beginning to observe Higgs with B, but we did it. And the golden channel here is the VH production. It has a very small rate. But if one focuses on the leptonic decays of the W or the Z boson, then QCD goes down to negligible level. And the key point of the analysis is, as I said, focusing on leptonic decays of the Ws, develop powerful BZ reconstruction tools, both for tagging, but also for correcting the BZ energy, machine learning techniques for signal and background separation, and also very sophisticated background estimation techniques, usually relying on data because we have to fight with a very complex background composition. So, and this is a plot from Atlas that shows the first observation of Higgs to be B. It's shown with red. And the story here is that using run 1 and 2016-2017 data taking periods, run 2 data taking periods, the expected sensitivity was around a little bit more than 5 sigma. The observed was a little bit less than 5 sigma. And then by combining also other production mode, VBF, GGF, and TTH, this allows us to exceed the 5 sigma and have the first observation of Higgs to be B. Then, of course, with more data, we move from the observation and carried out precision measurement in the VH and also in other production mode. And new developments for round 2 data is, first of all, improvements in the signal extraction, Also the addition of the boosted jet topology, which for the final result is combined with the result topology. And this is important, particularly to probe the high PT regime. So in the boosted jet topology, the Higgs-to-BB candidate is reconstructed as a single large radius jets, and then dedicated double B tagging algorithms are developed to identify the presence of the two B's inside the jet. Techniques that improve the jet matrix reconstruction are explored, like the kinematic fits. And finally, the signal is extracted by fitting the invariant mass of the Higgs-to-BB candidate. This shown, the Higgs-BB is shown with red here. And to validate all the details, one measures the Z2BB that you see here with gray. A third development, run-to development, is to categorize events based on the PT of the Higgs, which, as shown earlier, they are sensitive to new physics, can be more sensitive to new physics. And having said all that, with the full run-to result, we have almost 7 sigma observation of Higgs to BB in the VH production mode. But what is more interesting to see is that actually we have an observation of specific, of individual production mode. In the ZH, we have more than 5 sigma observation. And for WH, we have 4 sigma. And on the right plot shows the results as a function of the PT of the W or the PT of the Z for the result topology, the boost topology, and the combination with green. Overall, things, at least up to now and within uncertainties, agree with the standard model expectation. And then we use these results actually to set constraints in the context of the EFT framework. So on the plot on the left, you see the impact on the production, on the VH production of different models on different Wilson coefficients. And some, for instance, affect only the Z's and not W's, like the blue one. But typically, you see that the modifications are more important as we go higher in the PT of the Z or the W. And this is, on the right plot, is an example of the constraints on some Wilson coefficients that are sensitive to the VH production. With blue is using the result topology, the yellow is using the boosted topology, and the combination of the two allows to further constrain this parameter. Now, in the VH channel, in the BB channel, we actually probed also other production modes, for instance, the VBF, which has the second largest production cross-section. And here, the signature is actually the 2 forward quarks that we use to suppress QCD. And another additional mode that was used also, the VBF in association with the photon, which also helps to particularly suppress further QCD background. And the usual suspect in this analysis is B-tagging and also machine learning techniques for the event classification. So the idea, in a nutshell, both production modes are explored. The idea is, in the nutshell, is to develop machine learning techniques to suppress the smoothly falling background, which is estimated from data, and then fit the invariant mass of the two B's to extract the Higgs signal that is shown here with red. The full analysis details are validated by measuring the Z2BP. Now, there are techniques on how to avoid scalping of the QCD background estimation, etc. I skip them in the interest of time. I'm skipping them, but feel free to ask me if you have questions on this topic. And concerning the results, this is the full run-to results. This is the plot on the left is without including the photon, the VBF plus photon topology. This is almost a 3 sigma, 2.8 expected, 2.6 observed. Combined with the photon, we have an observed and expect the same observe and expect significant, almost 3 sigma, 2.9. So this channel is coming also. And this is the compatibility, the signal strength compatibility between the different channels and the combined one, which within uncertainty is pretty consistent with standard model. And the last analysis I want to discuss on the Higgs to BB land is the inclusive Higgs to BB analysis, which is more sensitive, focusing more on the high PT regime. The idea here is to reconstruct the Higgs to BB candidate as a single large radius jet. So both B's are contained into the single jet. And clearly the challenge here is the overwhelming QCD background. So first of all, advanced machine learning techniques are developed to identify these two B's, right? That use low-level information like PF candidates and also advanced machine learning techniques. And another important point is also the calibration of the tagging. So thanks to the very large LHC dataset, the tagger is calibrated using Z2BB. So effectively, you do a cross-section measurement, ZBB cross-section measurement, and deviations from the expected value are the scale factors of the tagger, which you measure here and you apply in Higgs-BB. The last challenge one has to face is to predict to the QCD, the smoothly falling QCD background, and this is derived from data in the mass from the failed category. Now, moving to the results. So this is the signal strength in different regions of the PT of the Higgs. So inclusively, we have a signal strength that is around 2.5. It's a bit higher than the expected standard model value. And this particularly coming from the high PT Higgs regions. And just as a reminder, I showed earlier in the talk a plot that shows that new physics can impact more the high PT regime. Of course, I'm not claiming something, we need more stats for more firm conclusion, but to make it also a little bit more interesting is that Atlas has also a similar analysis that sees also a trend compared to the standard model value. Of course, it's difficult to compare the two analyses because the uncertainties, particularly in the Atlas side, are much larger. But definitely, this is something that we should keep an eye on for run 3, and also we should also actually sync on the beams of the PT6. So something to keep an eye on for run 3. And then the next stop is Higgs to measure the Higgs-charm quark coupling. So if Higgs to BB was, this is an event display. So you have, this is in the VH production mode, the Z became to 2 muons and Higgs became to 2 charm quarks. So clearly, if Higgs to BB was challenging, imagine how Higgs to charm is challenging. The motivation is clear. We want to establish couplings to up-type second generation quark. But as I said, this is clearly very, very challenging at the LHC. C tagging is more difficult than B tagging. And also we have to deal still with very large background, and this analysis Higgs to BB is a background, right? So clearly we need novel tools and techniques and lots of data if we want to start probing the standard model values for Higgs-charm coupling. Now, let me take a step back, because as I said, this is challenging. We have to do quite some improvements in the jet, particularly in the jet tagging front. And this is, jet tagging is it's a cornerstone for multiple Higgs analysis and of course of Higgs OCC. And in order to have powerful jet reconstruction and verification, the key ingredients are, first of all, the input variables that we are using, how we are representing the jet, and also how we design the machine learning algorithm. And I'll go very briefly in these 3 steps. So first of all, what is a jet in a theory? So in theory, a jet is a spray of particles that are produced by the hadronization of quarks and gluons. Experimentally, and I have an event display here, a jet is a cone of reconstructed particles in the vicinity of the initial particle, right? Now, in order to explore more of the detector's potential, we need to go to particle-based jet tagging. And this we can do because both, as I said earlier, all LHC experiment has some flavor of particle flow algorithm, which provides a list of particles, a very rich set of information per particle. So you can have information related to energy, momentum, position, the displacement, etc. So on average, we have something like 50 properties per particle. And then depending on the jet type, we can have 50 to 100 particles per jet. So we're talking about 1,000 inputs per jet. So this is an ideal case for advanced machine learning algorithms using low-level information. So this is the input. The second part, as I said, is the jet representation. So the notion of point cloud is existing in data science. So a point cloud is a set of data points in space that one can produce, for instance, for 3D scanners. So we have, let's say, an airplane here. These are represented the airplane as a point cloud, as a set of points. And then, for instance, we want to identify wings from the wings of the airplane. So we can use machine learning algorithms to group points based on their similarity. And you see them here, the wings are very similar, here and denoted with yellow. Or an even more exciting, probably example, the notion of point clouds is used from Google to design the self-driving cars, to identify other cars, people, buildings, etc. So then, can we use the question, and what actually we did is actually, can we use the notion of point clouds also for jet physics, for jet tagging? So moving from point clouds to particle clouds. So a particle cloud is a set of particles in place, and the jets are produced, which are produced by clustering a large number of particles from the detector. So based on this, we developed ParticleNet, which is a novel algorithm that uses an improved jet representation and also network architecture. The inputs are particle flow candidates and secondary vertices. The output is a multiclass. I believe you have seen this already, so I'm not going to go in detail. But you can imagine the main points here is that we are treating the jet as a particle cloud. And you can imagine the particle cloud as a graph in computer science. So each particle in the graph is the vertex of the graph, right? And then interaction, the red lines here between the particles, are the edges of the graph. And then in order to do jet tagging, we actually follow a hierarchical learning approach. First, we learn local structures by identifying the neighboring particle. So we update this graph 2-3 times by grouping particles based on their proximity in some kind of high dimensional space. And then we move to more global features. So this is the meat, let's say, of the ParticleNet algorithm, which is not only used for jet tagging, but also for jet mass regression. And as you have seen, jet mass is one of the most powerful observables to discriminate, for instance, Higgs-bottom jets from background jets. But it's very sensitive to soft radiation, pileup, etc. So what we're typically doing, we're using grooming techniques like soft drop to remove soft and wide angle radiation. Now, this is simple and very well tested, but has some inefficiencies. And you can see on the plot on the right, for instance, the orange line, which corresponds to the Higgs boson, that we have cases where the mass is very low or very high, right? And particularly in the case of where we have Higgs decay into BB and CC, we have an additional challenge, which is the energy lost by the undetected neutrinos. So to overcome this, we develop a regression algorithm based on ParticleNet, the same architecture, the same inputs, the same representation, but instead of doing classification, we do a jet mass regression. And you see the regressed mass with green, which is very close to the target mass, compared to the much closer to the target mass, compared to the red one, which is the algorithm used in the past. So putting all these pieces together, on the left is the performance, the improvement in performance in the identification, for instance, in Higgs to charm against BB background or against the full soup of V plus Z. So overall, we see an improvement of this new jet tagging algorithm, factor of 4 to 5 compared to the previous state of the algorithm, and also improvement in the jet mass resolution by a factor of 2. And these were one of the first analyses that used these tools is the CMS search, the full run 2 CMS search for Higgs to CC. The idea here is to exploit as much as possible the Higgs decay topology. We have the more traditional resolved Z topology where each Higgs candidate is reconstructed as 2 small radius jets and gives us access to a large fraction of the available cross-section. But also this analysis introduced the merge jet topology, where first of all, where the two charm candidates are reconstructed, the two charm quarks are reconstructed as a single large radius jet. And this has advantages. First of all, allows to better exploit the correlation between the two charms since they are in the same jet. Has improved reconstruction efficiency, as you see on the plot here, which shows the reconstruction efficiency as a function of the decay of the Higgs. So you see above 200 and 300 GeV, the reconstruction efficiency is higher than the more traditional resolved jet approach, and allows to use also these state-of-the-art tools like ParticleNet. Now, without going to the details of the analysis design, the analysis focuses on three categories based on the leptonic decays of the W boson, and then advanced machine learning techniques are also used to improve the event level separation. Now, moving to the result, on the left shows the invariant mass distribution of the large radius jet. So before going to the actual the constraints on the Higgs-charm coupling, let me tell you that the full details of the analysis were validated by measuring the VZ to CC process. And we have an observation of Z to CC of 5.7 sigma compared to 5.9 sigma expected. And this actually, and the signal strength is consistent with 1 here. So, and this actually consists the first observation of Z to CC in a hadron collider. And then on the right side, I have a plot that shows the upper limit on signal, the 95% upper limit on signal strength, where the combination of the merge jet and the resolved jet topology shown here yields has an observed upper limit of around 14 times the standard model value for around 8 times expected, and a mu of almost 8 times the standard model, plus or minus 4, which is consistent with standard model value of less than 2 sigma. And we used the result actually to set the tightest constraints on kappa C. The expected is smaller than 3.4. The observed is between 1.1 and 5.5. As I said, these are the tightest constraints on kappa C. And so concerning the prospects on this very challenging Higgs to CC analysis, actually, we started here, a few thousand times the standard model value, and we are now at the case in the situation where it's around 8 times the standard model value. So in the last 5 years, we have a very dramatic improvement in the sensitivity of this in measurement the Higgs-charm coupling. Of course, this comes with lots of effort and innovation in multiple areas, in instrumentation, in physics object reconstruction, and also in analysis techniques. And to give you also some more hope, we carried out also some projections for the high luminosity LHC. And we extract simultaneously the signal strength for Higgs to CC and Higgs to BB. And to make the long story short, with high luminosity LHC, we will start reaching without any other improvements in analysis, we'll start reaching the standard model sensitivity. And a very hot off the press result, an additional production mode for Higgs to CC is focusing inclusively, targeting an inclusive production of Higgs to CC, similar to Higgs to the Higgs to BB analysis. The analysis targets the high PT regime. Again, here also the Higgs to CC reconstructed as a single large radius jet. Key points here is the CC identification, the estimation of the QCD background, and this results actually to an upper limit of observed 45 times the standard model, 38 observed, and the signal strength is consistent with the standard model values. Still, it's far from the sensitivity of the VH analysis, but provides its completely orthogonal analysis compared to the VH. Now, another angle to constrain the... Is there a question?
Question, Lucas.
Yes.
How do you distinguish between a big quark? I mean, this single large jet, as you're mentioning, this single large jet is containing either the both B quarks or either the C quarks. So for the B quark, the characteristic property is that, like, the secondary vertex, from where you kind of like reconstruct, right? So in case of C jets, like how you're going to identify them, like and what kind of a strategy are you going to use? I mean,
so these are estimated. So yes, the main handles. I mean, so here the output is a multi-class. So the Higgs. I didn't go into these details, but we have a class that simultaneously figure out if it's a BB, CC, etc. These are, you can consider as probabilities. Now, the main handles we have is clearly the presence of secondary variables or displaced tracks, right? BB it's easier because you understand the question. BB it's easier because you have actually you can have two displaced vertices, one from the B to charm and another from charm, right? From the charm. In CC is you have only one displaced vertex. So, but that's why this is also reflected on the performance, which in case of BB, the performance, the separation between, let's say, BB and light and QCD jet is better than compared CC to light jet. But exactly, the main information is the displacement of the particles for flavor tagging. But is this, because I couldn't hear you very well, this was your question, or how we separate?
Yeah, partly I have answered my question. I also have a couple of other questions, but I would like to conclude this like one question, like, do we have any common platform, because this strategy will be employed in both Atlas and CMS. Are you people having any common platform that's working together for this framework, like where the to improvise the speed tagging, particularly in this boosted regime?
So this algorithm is used in CMS, both in multiple analysis now, the ParticleNet, also be tagging, for instance, in the Higgs searches, etc. Atlas hasn't used it yet, but they will use it. Actually, last week I was in the Higgs pair workshop and I was discussing with Atlas colleagues, and they are very interested in using it. Yeah, but
because when I attended like some of these FCC PD monthly meetings, I came across like that they set up like some framework, like which is like kind of inter-experimental setup where they can work on it. So that's the reason.
Complete the seminar.
Sure. Okay, yeah.
And Lucas, you have 2 to 3 minutes. If you can finish.
I will go very fast. Now I'm almost done. I wanted to mention that in addition to the direct searches that I showed earlier, there are also other angles that we can constrain couplings to charm and also lighter.
You can block it and clone
lighter quarks. So, for instance, we can use charmonium decays. So I have an example here where we have the J psi and the gamma. And the idea here is to constrain kappa C from this process. In the interest of time, I'm skipping the details of the analysis strategy. But bottom line, these are the sensitivity here. The constraints are much higher, much looser than the constraints we have from direct search. It's around 100 times the standard model. Potential advantage of this exclusive decay is actually that we can probe lighter quarks like strange and U and first generation quarks, like having the Higgs decay into a psi and gamma, or a Higgs decay into a rho and a gamma for the first generation. And these are examples from CMS in this analysis, but still we are very, very far from standard model values. We are under 500 times the standard model values here. And the last part, the third route that we can use in these measurements actually to constrain kappa C and other couplings is actually using indirect constraints. So we can exploit, for instance, the differential measurement, the PT8 measurement, Higgs measurement from other Higgs decay modes, for instance, gamma-gamma and the 4 lepton channels to constrain kappa C. And you see on the plot on the left, different values of kappa C, how they affect the PT of the Higgs. So on the experimental side, this is an example from Atlas in the Higgs to gamma-gamma channel, we have the observed data, we have the the solid red line corresponds to the standard model value of kappa c equals 1. And then we try to use this data to set constraints on kappa c. And using this information, using the gamma and the 4 lepton channels, we can achieve constraints of kappa c smaller than 11 times the standard model value. This is uses only, the atlas uses the full run 2 analysis, and these constraints are less sensitive compared to the direct sets. But this provides also another angle of measuring kappa c or constraining kappa c. And even further, one can have constraints on Higgs quark couplings using a grand combination of all various production modes and Higgs decay modes. And just to highlight here that the constraint one can achieve with this grand combination is on kappa b is around 0. The kappa b measure is 0.8 plus or minus 10, around 10, and on kappa t on the Higgs-top coupling is around 0.9 plus or minus 10, which are consistent, a bit lower, but consistent with standard model value. And the negative kappa t, the negative sign kappa t is excluded using this result by more than 4 sigma, is disfavored by more than 4 sigma. And I think since I'm running out of time, I'll just very briefly say that
okay, you are okay with
I leave the summary here, and I'm happy to take questions.
No, Lucas, you can give the summary. You have enough time. You can go through the.
Okay, yeah. So then, just to conclude here, executive summary. We established top Higgs coupling, bottom Higgs couplings, and we are going after now CERN Higgs coupling. We have a very complete checklist. We have exploring multiple production and decay modes. There are still run 2 results in the pipeline, and of course, we have the run 3 results that the upcoming, looking forward for run 3. Now, there has been enormous progress in measuring the Higgs particle properties. And this progress both on the experiment side, Atlas CMS, and also in the theory community to reduce the uncertainties. On the experimental front, there are improvements in very many areas, like on the detector side and the calibration and the object reconstruction, and also using and developing and using sophisticated analysis techniques. And also, compared to what we had in the past, we have extended interest to also exploring additional topologies that were not accessible before. And clearly, all these efforts pay off. We have seen substantial improvements in the sensitivity of the analysis, very often reaching or even exceeding the sensitivity that we expected with much more data, high luminosity LHC. Now, as it is now, within the uncertainty that we have, everything looked very standard model-like in the Yukawa sector. But we have run 3 coming, and combined with the run 1 and run 2, we're expecting to have order of 500 centimeter of data. And I think we should still keep studying exhaustively the Higgs properties. Thank you very much. And I'm happy to take questions.
Thank you.
Any questions or comments? Yeah, Soumya, you can go first.
In your slide number 42 or 43, where you were showing that the GGH to H to BB in the boosted regime.
40.
Yeah, this slide is okay. So you can see that there is a huge difference between the observed and expected. So is this any worry from, is there any, what actually the difference signifies here? 2.5 sigma from observed, and whereas expected is very low, 0.7 sigma. So from the data, we are just overestimating the signal, right?
Yes. So the thing is here, so there has been a lot of study here to understand this excess and see, for instance, if it's coming from the calibration of the target. I don't have this plot, but actually the target, this same plot, this is for Higgs, was done for the Z's. So, and there is spot on because we use the Z's to calibrate the target. Other thing that was tested was to to see what's the impact of different Monte Carlo generators. So again, this was not covering this difference. So I think, I mean, could be something else. I mean, we did a lot of studies. We didn't find a smoking gun. Could be, for instance, I don't know, could be new physics, maybe. Could be unlucky, very unlucky statistical fluctuation. I think we have to wait with more data.
And okay, so if we compare these number with the Atlas number, I mean, if we can compare this, I mean, the significance, it is a 3.7 from the CMS and 1.1 from the Atlas. So from the Atlas is very well, I mean, within the, I mean, the standard model prediction, but the CMS is not, right? I mean, if you can add the uncertainty as well.
So uncertainty is as much larger in Atlas, right? 3.64. So you see it here. This is the bin. So we don't have the same binning, but so this is 1,000. So this is, you know, we don't have the same binning, so it's not easy to compare. But within, I mean, okay, you cannot. Maybe there is a trend. Of course, it's not easy to say with the Atlas case because the uncertainties are very large. But I think that's why I'm saying we just have to wait, and maybe we should also synchronize with Atlas and have the same binning and probably much more. I mean, they should also improve their uncertainties in this last bin. So, but yes, inclusively, it's very consistent. Atlas is very consistent one, but you see the uncertainties is much larger in the Atlas case.
Okay, another one, a small question from your slide number 50, or where you have shown the different multi-class score for the individual processes. Yes, like here. So this is not mentioned here, but we know that there are these two scores. One is the mass correlated ParticleNet score, Higgs versus QCD. Another is the mass decorrelated score for the Higgs versus QCD. Can you give any idea? I mean, what actually the difference of the training when you are getting that mass correlated or mass decorrelated scores?
Yeah, so I didn't have time to discuss the thing, but let me tell you in words, and I can also privately message you with more detail. So what we do, this is the architecture for the mass correlated and mass decorrelated target is the same, the ParticleNet architecture, the same inputs, etc. What we do in the case of mass decorrelated, in the mass decorrelated case, and this is new only for ParticleNet, is actually we have produced a dedicated set of training samples that effectively produce having Higgs bosons with different masses from 10, 15 GeV to 300 GeV with a very granular selection on the mass. And this we use as input samples for the training. So we give a set of samples that are mass agnostic. So this way, the algorithm cannot rely on the mass to achieve discrimination. For the nominal version, the mass correlated, we use the standard samples that we use in CMS.
Okay. So that means that mass decorrelated score is important for the off-shell W production, right? I mean, for the W star.
Yes, in general, you know, there is a caveat here that the mass decorrelated works for Higgs ZW and for QCD. For top, one has to do another technique to decorrelate because it makes the fact that we have also the W in the case of the top decays makes it more complicated, and we have to think how to, with samples, how to produce the samples. But for two-pronged, like W, Z, Higgs, etc., yes, I would recommend to use the mass decorrelated version for off-cell W's, etc.
Okay, thank you, Soumya. I think we should go to the next question.
Sure. Yes, I'm done. Yeah.
Ajani, ma'am, did you have a question?
Nice talk, of course, with us. Can you please check on this slide itself? How do we choose this xi? So you this edge convolution, etc. you are doing this slide only.
Sorry, because something happened. Let me try to share again. Sorry, something happened. I cannot see my screen. Okay, can you see now?
We can see.
Yes, can you please repeat your question?
Yeah. because I don't know much about this. So how exactly do we choose which is xi? Which should be my xi? The edge convolution, what is happening? How do you do it?
So you mean here what the convolution is here?
Yeah.
So this is
The technique you use to.
yes. So the idea here is so when
My point is that this green point or whatever you call it, does it is it supposed to contain some particular properties?
so each particle here
Yeah.
has a set of features, a set of properties that around 40, 50 properties. And based on these properties, let's say we want to find the closest neighbors, or let's say we have this blue particle here. So we want to find the closest neighbors to this particle. Closest means not necessarily in distance, but closer in some high dimensional space based on the features that we have.
Yeah.
If you want to do bit tagging, you want to find the tracks that come from the same vertex. So what we do is we use the properties assigned for each particle. We estimate also the relations and the interactions between these neighboring particles. And then we update the graph. So initially it was these particles, the closest neighbors. Then using this edge convolution, the convolutional operation, as we do like in 2D images or in series like 1D convolution, we find which are more relevant particles and we update the graph. So the particle stays there, but these neighbors, this light blue, can change. And this we do it 2-3 steps, which we find it's sufficient to achieve good performance. So this is what the reason we use this convolution is to better find the neighbors of each particle.
So this green point, xi prime, it is supposed to have some particular properties, not necessarily. That is
No,
only.
Yeah, every particle has the same features, the same properties, displacement, energy, etc. But then we use these properties and also relationship between the particles to identify which are the closest particles. Like, let's say you have a displaced vertex, you want to have the tracks, let's say in the B, we have an average 5 charged particles.